A team at Peking University just ran an AI task 149 times faster than a commercial GPU. Not with a bigger chip, not with more servers, with less than 1/9 the computing power. And the whole thing took 105 microseconds. That is not a typo. To put that in terms you can feel, 105 microseconds is roughly the time it takes a single frame of a 60 frames per second video to flash on your screen. The GPU doing the same job took 15.6 milliseconds. In the world of computing, that gap is enormous. That is not a rounding error. That is a different category of machine. And here's what makes this story strange. The system that won was not a supercomputer. It was not a room full of servers stacked to the ceiling. It was 5 chips. 5 off-the-shelf programmable chips of the kind used in missile guidance systems and self-driving cars. Connected not by copper wire, but by light. The paper was published on May 19, 2026 in National Science Review, a peer-reviewed journal published by Oxford Academic. The corresponding authors are Professor Wang Xingjun, Vice Dean of the School of Electronics at Peking University and a Fellow of the Optical Society of America, and Dr. Haowen Xu, an Assistant Professor at the same school. This was not a press release. This was not a company announcement. It was peer-reviewed science. Before we get into it, if you enjoy videos like this, hit the like button right now. These take a serious amount of research and time to put together, and every like pushes this to more people who would love it. Subscribe if you are not already, and turn on notifications so you do not miss what comes next. Now, to really understand why this result matters, we need to start with a problem that has been quietly choking the entire AI industry for years. The problem has a name. Engineers call it the memory wall. And once you understand what it is, the Peking University result stops looking like a curiosity and starts looking like a direct answer to one of the most stubborn limits in modern computing. Right now, in every data center running AI, the same thing is happening. A neural network processes data in layers. Think of it like an assembly line where each station does one job and then passes the work to the next. Except on a standard GPU, that is not what actually happens. Layer 1 finishes its job. Then it writes its output to memory. Then it stops and waits. Layer 2 reads that output from memory, does its job, writes to memory, stops and waits. Every single layer, write and wait, write and wait. The processor itself, the part doing the actual math, sits idle during every one of those waits. It is like having a factory where each worker finishes their part, puts it in a box, walks the box to a warehouse across the street, and then stands there until the next worker walks over, picks up the box, and brings it back. The warehouse is memory, and the walk back and forth is time you cannot get back. The standard answer from the AI industry has been to add more GPUs, buy more chips, build bigger data centers, spend more money, and that works up to a point. But the wall does not move. More GPUs means more of the same bottleneck, just running in parallel. You are not solving the problem. You are hiring more workers who all have to make the same walk to the same warehouse. The energy cost alone is becoming hard to ignore. Data centers running AI already consume a significant and growing share of global electricity. The authors of the Peking University paper wrote directly that their design can help cut unsustainable energy usage in data centers. That is not a marketing claim. That is a description of what happens when you remove the memory read-write cycle from the equation. Here is the thing. The team at Peking University did not try to make the GPU faster. They did not try to build a better warehouse. They asked a different question entirely. What if the layers did not have to wait at all? What if the output of layer 1 went straight into layer 2? No memory write, no memory read, no pause, like a real assembly line where the part slides directly from one station to the next without ever touching a shelf. That is what light lets you do. Light travels through an optical fiber at roughly 200,000 kilometers per second inside the cable. The signal does not degrade the way an electrical signal does over a copper wire. It does not generate heat the same way. And critically, it does not need to stop at a memory address before moving on. The optical link in this system carries data at 400 gigabits per second. The output of each chip passes directly to the input of the next one. The assembly line runs continuously. To build that assembly line, the team designed 2 custom pieces of hardware. The first is a silicon photonic transceiver chip. Its job is to convert electrical signals, the kind chips speak in, into pulses of light and then convert them back again at the receiving end. It does this at 400 gigabits per second. For context, a typical home internet connection runs at somewhere between 100 and 1000 megabits per second. This chip moves data at 400,000 megabits per second, per chip. And the team confirmed error-free transmission at that full speed, with no optical amplification, meaning no extra hardware needed to boost the signal along the way. The second component is a 16 by 16 non-blocking optical switch chip. Think of this as a traffic controller for light. It can route signals between any combination of 16 inputs and 16 outputs simultaneously without any one path blocking another. The total signal loss across the switch is no more than 5 decibels at the 1300 nanometer wavelength the system uses. That is a record low for a switch of this kind, and the aggregate switching bandwidth it supports is up to 6.4 terabits per second. 6.4 terabits every second. Now here is where the benchmark result comes in, and why the numbers are worth sitting with for a moment. The team connected 5 FPGA chips using this optical network. FPGA stands for Field Programmable Gate Array. These are chips that can be reprogrammed to do different tasks, which is why they show up in everything from radar systems to autonomous vehicles to financial trading platforms. Each of the 5 FPGAs ran one layer of a 5-layer convolutional neural network. Layer 1 on chip 1, layer 2 on chip 2, and so on. The output of each chip passed directly to the next one through the optical link. No memory stop, no waiting. The task was to process 1,000 images from the Fashion and NIST dataset. Each image was 32 by 32 pixels in 32-bit floating point format, which works out to 32,768 bits per image. The network's job was to strip noise from each picture. It is a standard AI inference task, the kind of thing that runs millions of times a day in real AI systems. The optical system finished all 1,000 images in 105.16 microseconds. The commercial GPU, rated at 16.96 teraflops, took 15.6 milliseconds for the same job. That is 148 times longer, nearly 149 times slower. And here's the part that should stop you cold. The 5 FPGAs combined delivered 1.969 teraflops of raw compute. That is 11.6% of what the GPU could do on paper. Less than 1/9 the raw power. And the optical system still finished the task 149 times faster. The reason is efficiency. The optical system ran at 94.7% of its theoretical peak the entire time. The GPU could not say the same, because the GPU kept stopping to talk to memory. The FPGAs never stopped. The light kept moving. Think about that for a second. The winning system had less than a 1/12 the raw computing power. It won by 149 times, because it never had to wait. Here is where it gets uncomfortable for the people watching this from Washington. The Peking University system does not need leading-edge chip fabrication. It does not require the most advanced lithography machines, the kind made by ASML in the Netherlands that the United States has spent years restricting China's access to. The silicon photonic transceiver and the optical switch chip are built on mature fabrication nodes. Standard processes, the kind of manufacturing that has been around for years and is not subject to US export controls. This matters because of what the United States has been trying to do. Since 2022, the US government has placed progressively tighter restrictions on the export of advanced AI chips to China. The NVIDIA A100 was restricted, then the H100, then the H800. The logic was straightforward. If China cannot get the most powerful AI chips, it cannot build the most powerful AI systems. Analysts at the Center for Strategic and International Studies have specifically flagged silicon photonics as a front in US-China technology competition for exactly this reason. China is building a path around the wall by working on the connections between chips instead of the chips themselves. At the OFC 2026 conference, NVIDIA's own statement captured the shift in industry thinking. The data center is a computer and the network defines its boundaries. That was not a Chinese company saying that. That was NVIDIA. The consensus among people who build AI infrastructure is moving in a clear direction. Raw compute is no longer the binding constraint. The connections between chips are. And the Peking University result is a direct demonstration of what that means in practice. China cannot easily get the H100, but it can build the road the H100 travels on. And if the road is fast enough, the speed of the car matters less. Now, this is the part of the story where it is worth being honest about what this system is and what it is not. The paper is clear. This is a laboratory prototype. The benchmark task, a 5-layer network on the Fashion MNIST dataset, is small by the standards of modern large-scale AI. The models powering ChatGPT, Gemini, and similar systems have billions of parameters and require thousands of chips working together. The Peking University system used 5. The authors themselves acknowledge that the GPU comparison involves a relatively modest workload, and that the result needs to be proven at larger scales before anyone can claim this changes data center architecture. There are 3 things the team lists as next steps. First, miniaturization. The current system is a lab setup. Getting it small enough to fit inside a real server rack is a real engineering challenge. Second, long-term reliability. Optical systems in a data center have to run continuously for years without degrading. That has not been tested yet. Third, performance at cluster scale. 5 chips is a proof of concept. Thousands of chips connected optically is a different problem. The physics get harder, the switch complexity grows, the heat management changes. None of that makes the result less real. The 149 times speed advantage is not in dispute. The 94.7% efficiency is not in dispute. The peer review in National Science Review is not in dispute. What is in dispute is whether a laboratory result translates cleanly to commercial infrastructure, and the honest answer is not yet. But here's the thing about laboratory results. Every technology that runs the modern world started as one. The transistor was a lab curiosity in 1947. The internet was a government experiment in the 1960s. Fiber optic cables, the same basic technology underlying this research, were a laboratory concept before they became the backbone of global communications. The question is not whether a lab result matters. The question is how fast the gap between the lab and the data center closes. The team behind this paper has a track record worth paying attention to. Professor Wang Xingjun was listed in Stanford University's World's Top 2% Scientists in 2023. He was elected a Fellow of the Optical Society of America in October of that same year. His research group at Peking University has published extensively on optoelectronic integrated chips and silicon photonic systems. Dr. Haowen Xu joined as an assistant professor with a focus specifically on optical interconnects. The co-first authors on this paper, Zihan Tao, Yan Zhou, Weizhen Yu, and Huajin Chang, each contributed either to the chip design or to the AI algorithms that make the pipeline work. This is not a single inspired experiment. It is the output of years of coordinated work across hardware and software at the same time. That coordination matters. One of the things that makes this system work is not just the optical hardware, it is the algorithms. The team designed inference algorithms specifically for this architecture. The neural network was partitioned so that each layer maps cleanly onto one chip, and the data flowing between layers is formatted to move efficiently through the optical link. The hardware and the software were designed together, for each other. That co-design is part of why the system runs at 94.7% of theoretical peak. Most systems, even well-engineered ones, run at a fraction of their theoretical maximum because the software was not written for the specific hardware it runs on. This team wrote both. And that approach, designing the algorithm and the hardware as one system rather than 2 separate problems, is increasingly where the frontier of AI performance lives. It is not just a Peking University idea. NVIDIA does it. Google does it with its TPU chips. Apple does it with its neural engine. But all of those systems still use copper wires between chips. The Peking University result is the first peer-reviewed demonstration, at this scale and with this level of detail, of what happens when you replace those copper wires with light and build the algorithm around the new physics. The conventional wisdom in AI infrastructure for the last several years has been simple. You need more compute, more GPUs, more power, more money, The data centers being built right now to run AI consume as much electricity as small cities. Microsoft, Google, Amazon, and Meta have each announced data center investment plans in the hundreds of billions of dollars. The assumption underneath all of that spending is that more hardware equals more capability. The Peking University result does not say that assumption is wrong. It says it might be incomplete. If the bottleneck is not the chips but the connections between them, then at some point adding more chips stops being the right answer. You are building a faster car on a road that cannot support the speed. The optical interconnect is the road. And if light can replace copper at scale, the economics of AI infrastructure change, not a little, structurally. You could, in theory, run a system with less raw compute, less power, and less cost, and still outrun a system with more of everything, because the light between chips never stops to wait. That is what 105 microseconds versus 15.6 milliseconds means in practice, not just a faster result on a test. A different way of thinking about what speed in AI actually requires. The team's next steps involve co-packaged optics, higher speed silicon photonic transceivers, and faster input-output rates on the AI chips themselves. Co-packaged optics means integrating the optical components directly onto the same package as the compute chip, rather than connecting them separately. That is where the miniaturization challenge gets solved. Several major chip companies, including Intel and Broadcom, are already working on co-packaged optical designs for data center networking. The Peking University work is not isolated. It is part of a broader shift in how the industry thinks about chip-to-chip communication. The difference is that the Peking University team has now demonstrated in a peer-reviewed paper what the destination looks like when you take the optical path all the way to the AI inference layer. The paper was picked up internationally within weeks of publication. South China Morning Post, Vien Express, Interesting Engineering, eWeek, Electropages, and Eureka Alert all covered it. The coverage noted the silicon photonics angle specifically in the context of US export controls. That is not an accident. The strategic significance of building high-performance AI infrastructure on fabrication nodes that are not restricted is exactly the kind of thing that gets attention from analysts who track technology competition between the US and China. The future of AI speed was not decided by adding a faster chip. It was not decided by building a bigger data center. It got decided, at least in this experiment, by asking whether the wire between the chips needed to be wire at all. And now every team building AI infrastructure has to look at that 149 times number and decide what to do with it. If you had to choose, would you rather have the most powerful chip money can buy or the fastest connection between cheaper chips? Drop your answer in the comments below. I read every single one.